we've learned about digital design theory, VHDL syntax, and how to run simulations. Today, we'll be working with real hardware. In this video, you'll build and deploy 4 VHDL designs on an FPGA: a single LED, an LED strobe, an LED sweep, and an LED binary counter. Welcome to the world of digital design. This is Metastable. For hardware testing, we'll be using the Basis 3, which uses a Xilinx AMD RTX 7 FPGA. Our Basis 3 board comes with 16 LEDs that we can program. For our first hardware test, let's try turning on a single LED. Let's start by creating our VHDL file, which we'll name led_test.vhd. First, we'll include the IEEE library and the standard logic 1164 package. After that, we'll define our entity. For now, the only port we need is a connection to an external LED, so we'll call that port LED. It'll be an output port with a standard logic data type. Something I should mention is that VHDL is a case-insensitive language, so these would all be considered the same identifier. For the architecture, we have nothing to declare. Our design will be extremely simple. All we need to do is assign LED to 1. This should keep our LED on indefinitely. With that, we have the HDL all set up for hardware testing. The next step is to connect this design to the actual hardware. We know our design's entity allows us to communicate with external hardware, but how do we actually make that connection? For this, we need something called a constraint file. A constraint file lists all the external pins and clock resources on the FPGA. By mapping those pins to the ports in our design, we create the link between the physical hardware and our HDL. Diligent, the maker of the Basis 3, has an official GitHub repo with the Basis 3 master constraint file. We'll want to download this. I'll leave a link to it in the description. Now let's take a look at the constraint file itself. Each line corresponds with a specific pin on our FPGA. For each line, we have the pin name, the pin standard, and the port connected to that pin. Currently, these statements are not being used, but we can uncomment statements we need by removing the pound symbol from the beginning of the line. Let's make a copy of the constraint file and place it in our working directory, since we'll likely reuse it in future projects. Let's rename it led_test.xdc, where XDC is the file extension for Vivado constraint files. Next, scroll down to the LED section and uncomment the line for the first LED. By default, the port is named LED0. The brackets indicate that this is the 0th or first element of an array. Here, we'll replace LED0 with LED to match our port list. If you're following along with a different AMD-based board, the process is the same. Just be sure to check the board's documentation to confirm that you're assigning the LEDs to the correct pin. To load our HDL and constraint files onto the board, we need to download and use Vivado. I should mention up front that Vivado is massive. Depending on the installation options you choose, it can take anywhere from 75 to 120 gigabytes.
Don't do it to me. I beg you. No.
Make sure you've got plenty of free space on your drive before installing it. Skipping the Vitis installation will save a significant amount of space, and we won't be using it in this course anyway. The download can also take a while, so be aware of that as well. You can find a link to the Vivado download page in the video description. Once downloaded, you should see this screen. From here, we'll create a new Vivado project. We'll give it the name led_test. Next, we'll verify the location that we'd like to use for our project and click Next. Here, we'll select an RTL project. Next, we'll add our design file, led_test.vhd, and change our target language from Verilog to VHDL. Here, we can add our constraint file. We'll need to select our hardware target, which we can do by going to the Boards tab and selecting the Basis 3. Vivado projects are based on the specific hardware you're running. With our RTL and constraints added and our board selected, we're ready to create our project. From here, we'll need to run both synthesis and implementation for a bitstream. Conveniently, we can also just click on the Generate Bitstream button to run all the prerequisite tasks. Once the bitstream successfully generates, we're ready to open the Hardware Manager. Here, we can open up a target. We'll connect our Basis 3 to our computer over USB and power on the device. Once we click Auto Connect, Vivado should now be able to find the device. You should see a device named XC7A35T_0. This is our FPGA. We can now program the device. Vivado should bring up our latest generated bitstream. Let's take a look at our board. And there you go. We can see that our LED is lit up. You've now programmed your first FPGA. You should see a new Vivado folder in your directory that contains all of your project and generated files. Notably, .runs contains our bitstream, and the .xpr file is our Vivado project file. Now let's take it up a notch. Let's try and make the LED blink every half a second. Now the first thing we'll do is add a clock port to our design. Next, in the architecture, we'll create a counter signal, count. This counter will help us deal with timing. The Basis 3's onboard clock has a frequency of 100 MHz, which means it oscillates 100 million times a second. We need some sort of way to bring down our clock rate to a manageable level. We can do this with our counter, which allows logic to occur at much slower intervals. The counter will be an integer. We'll give it a range of 100 million, so that the counter covers a full second. Since our range starts at 0, we'll end with 100 million minus 1. The range functionality limits our count value. Instead of counting past 100 million ticks, it will restart at 0. We'll also give it a starting value of 0. If you run this in simulation, you might get errors because of the way simulators handle range functionality. But Vivado should understand that we want our values to wrap back around to 0 after we've hit our range maximum. Because we're using a clock for synchronous timing, we need to add a clocked process. We also want all logic happening on the rising edge of the clock, so we'll add an if statement to check for that. 1 second for our clock is 100 million ticks, so if we want the light on for half a second, we want a transition when we reach 50 million ticks. We can implement this by starting a conditional where we check if the counter is equal to 50 million minus 1 or greater, and if so, we turn on the LED. If it's anything else, we turn the LED off. For VHDL, we can choose if we want parentheses around our conditional statements, as they aren't required like in other programming languages. I generally don't use them for functions like rising edge, but I do for regular logical assertions. I just do this because I think it looks nice this way. Outside of the conditional statement, we set the counter equal to the counter plus 1, so that on every rising edge of the clock, we update the counter. With our design implemented, we now need to uncomment the clock in our constraint file. We're now ready to rerun our design in Vivado. Once the bitstream is programmed to the board, we can check our new design. And there we go. It's blinking every half second. Let's kick it up another notch by testing all of our LEDs. One of the best ways to do this is by creating an LED sweep, where the LEDs are sequentially turned on and off for a brief period of time, and switch directions once we hit either of the end LEDs. To use all 16 LEDs, we could create 16 standard logic ports, or we could use something called a standard logic vector. Standard logic vector is another type that is defined in the Standard Logic 1164 package. Standard logic vectors allow us to keep related data together in an array of standard logic bits. They are extremely helpful when you're dealing with large groups of related binary data. Let's turn our LED port into a standard logic vector. We can do this by adding _vector to our port. In addition to this, we'll want to give it a range. We will make it a 16-bit vector by specifying 15 down to 0. This means that if we were looking at all the bits, Bit 15 would be our leftmost bit, and bit 0 would be our rightmost bit. Part of the reason we're using a standard logic vector in this situation is that our LEDs are already set up to be used as a standard logic vector. Each bit in our vector corresponds to an LED on the board. So if standard logic vector bit 0 is a 1, then LED 0 is turned on, and so on. Now we need to figure out the logic to get the LEDs to sweep. We'll need some mechanism that will allow us to control the index of which LED is on, and the direction of the sweep. We can begin by adding an integer for sweep direction, with a starting value of 1 for a positive direction, and an integer index with a starting value of 0 to start at the first LED. Let's think about what we actually want our LEDs to do. First off, we want one LED to be on at a time, with all of the others off. After a certain period of time, the next LED will light up. If we're at either of the end LEDs, we want to switch the direction of the sweep. The first thing we'll want to do is remove all the LED logic that we currently have implemented. Now, in our if statement, we're going to add another conditional. If our index is 14, then the direction is switched, and we assign that direction -1. Else, if the index is 1, then the direction is changed to positive. Effectively, what we're doing here is checking the index of the current LED to see if the next LED is at either end. We need to think one index ahead because by the time we hit the end indices, we'll need the new direction data. If we set it up correctly, we should have a smooth bounce from left to right and vice versa. In addition to this, we need to assign the index to the current index plus the direction. Next, we're going to assign the counter to 0, and move the other counter assignment into the else portion. This means that unless our target threshold is reached, we update the counter. If we hit our counter threshold, we reset the counter and shift which LED is on. We now have the logic that will increase and decrease our index and create the sweep, but we need to connect this to the LEDs. Outside of the counter conditional, we will assign our LED vector. We will first assign all of the LEDs to 0. We can do this by writing that our LED vector port is assigned others are set to 0. The others keyword is a way to reference all items in a grouping, which we'll use to set all the bits in our vector to 0. We will then turn on only the indexed LED. We can do this by writing LED of index is assigned to 1. The parentheses on a standard logic vector allow us to reference single bits individually. This will assign our LED the correct value, but we are assigning our indexed LED twice because others includes the indexed value. Since FPGAs run logic in parallel, how does this double assignment work? Signal assignments inside a process don't take effect immediately, like lines of code for a CPU. Instead, VHDL takes signal assignments and applies them at the end of the process. Inside the process, signal assignments are executed sequentially, but applied in parallel. So if you assign the same signal more than once, the last assignment will be applied. There are ways of making this signal assignment in just one line, but that's outside of the scope of this video. The last thing we'll want to do is change the counter threshold. 50 million ticks will look slow for our sweep, so let's speed it up from 1/2 to 1/20th of a second. This translates to 5 million ticks. You can also mess around on your own with this counter threshold to try different sweep speeds once you're able to confirm your design works. Now we'll update the constraint file to connect to all of the LED ports. This is done by changing our original LED port back to LED 0 and uncommenting the rest of the LED section. With that, we're ready to test. If we did everything correctly, we should be able to generate our bit stream and program the board. That looks like it's working. We get a smooth transition from left to right and vice versa. For our final test, let's create a binary counter with our LEDs. If you're unfamiliar with binary, I would highly recommend brushing up on how binary works, as we'll be working with it a lot in future videos. If I end up creating a video on binary, I'll link it in the description. A very brief overview of binary is that it's a system we can use to represent all numbers in terms of ones and zeros, which works great for digital machines. Binary is base 2. Every digit in a binary value represents a power of 2. So the first 4 digits would represent 2 to the power of 0, 1, 2, and 3, which convert to 1, 2, 4, and 8 respectively. To convert our binary value into decimal, we can take the power of 2 for each digit that is 1 or on and add them together. For example, if we have the value 1001, we can add 8 plus 1 to get our decimal value of 9. With that, let's build a simple LED binary counter. The first thing we'll need to do is add another package. The package we need to add is IEEE.numeric_standard.all. This package contains the unsigned data type. For our binary counter, we'll need to convert from an integer into a binary array. Unfortunately, we can't just convert straight from an integer to a standard logic vector. We first need to convert our integer into an unsigned. Standard logic vectors are arrays of bits, but we can't treat them like binary numbers. They are just a grouping of bits. An unsigned is an array of bits with an explicit numeric value and can represent any positive whole number. Going back to our example, the significance of 1001 for a standard logic vector is just that, an array with 2 ones and 2 zeros. Whereas for an unsigned, it's equal to 9, but in binary form. So we need to convert an integer decimal value into a binary value, and then convert that into a generic binary array. The first thing we can do is remove all signals besides our counter. Next, we'll add our binary counter value, val. Count here represents our clock tick counter, whereas val is an integer that will ultimately represent our binary value. Because we have 16 LEDs, we can represent 2 to the 16, or 65,536 distinct values, from 0 to 65,535, which will be val's range. The next thing we'll do is remove any logic that deals with the index or direction, as we'll now be dealing with the whole LED standard logic vector. Inside our counter conditional, we will add the statement val is assigned to val plus 1. If we reach our counter threshold, we add 1 to our binary value counter. If not, we simply increase our tick counter. Now outside of the conditional, we set our LED to this. This can seem complicated at first, but let's break it down. The first thing we're doing is adding our binary value counter val into a function toUnsigned, which takes integers and returns unsigned values. The second argument we give the function is the length of our LED standard logic vector. This is because an integer doesn't have any binary digits, so we need to tell our hardware how many bits we would like to use to represent our integer value. Once unsigned, we can then cast the data into a standard logic vector. One minor change is the clock counter threshold. For this specific test, 25 million ticks should work well. If we've set everything up correctly, our clock counter should count to our desired time at which we increment our binary counter value. This value is then converted from decimal to binary, and then directly assigned to our LED binary vector. Let's go check it out on hardware. After generating the bit stream, this is what we get. We are increasing by 1 in binary every quarter of a second. To get through all the values, it would take our board about 4.5 hours. But with that, you've run 4 unique designs on real hardware. That's all for this video. Next time we'll learn all about finite state machines with button debouncing. Leave a like if you enjoyed the video, and subscribe to stay up to date. See you in the next one.